It's stronger than steel, lighter than aluminum, and it's inside your car, your phone, your airplane, maybe even your coffee machine. But here's the part nobody talks about. The companies making this material have been quietly hiding something about how it's actually produced. Something that explains why it costs 10 times more than steel, and why most of what you think you know about it is wrong. Today, we're going inside to see exactly how carbon fiber is made. And trust me, it's nothing like what you'd expect. Here's something that'll change how you see this material forever. Carbon fiber isn't just a fancy substance used in Ferraris and fighter jets. It starts as something completely ordinary, almost embarrassingly simple. And by the time it becomes that sleek, impossibly strong final product, it's gone through a transformation so extreme, so energy-hungry, and so precise, that even a tiny mistake at one single stage can destroy the entire batch, worth thousands of dollars. Gone. Before we get into this, we want to be upfront with you. Everything you're about to hear is backed by real research. We went through manufacturing studies, material science papers, and industry reports to make sure this video gives you the actual truth. Not recycled headlines, not AI-generated summaries, not guesswork. Just the real process explained the way it should be. What you're about to see is the complete journey, from raw material all the way to finished carbon fiber, including the parts manufacturers would rather you didn't think about too hard. Coming up, we're breaking down every stage of the process. But there's one specific hidden truth about carbon fiber that the industry almost never mentions publicly. Something that explains the price, the scarcity, and why, even after decades of development, this material still hasn't replaced steel and aluminum everywhere. We'll get there. But first, let's start from the very beginning. So, what exactly is the thing manufacturers don't want you to know? We'll get there, but to understand it properly, you need to understand how this material actually gets built, because once you see the process, that hidden truth will hit you in a completely different way. Let's start at the very beginning, and I promise, this beginning is going to surprise you. Here's the thing nobody tells you up front about carbon fiber. That impossibly strong, incredibly light, premium material used in F1 cars and space shuttles. It starts its life as a type of plastic. Specifically, a polymer called polyacrylonitrile, or PAN if you don't want to say that 5 times fast. About 90% of all carbon fiber in the world today comes from this one material, and PAN is essentially a manufactured plastic fiber, the same broad category of material as the acrylic in cheap sweaters. Now, before you laugh, here's why this matters. PAN isn't your average plastic. It has to be chemically pure, extraordinarily consistent. Even microscopic impurities inside a single strand can weaken the finished fiber significantly. So producing high-quality PAN precursor is already a complex, controlled, expensive process before carbon fiber manufacturing has even started. And here's a number that puts everything into perspective right away. To produce just 1 ton of finished carbon fiber, manufacturers need roughly 2 to 2.5 tons of PAN precursor. That means more than half of what goes in never comes out. It gets burned away, expelled, eliminated during processing. So you're starting expensive and immediately losing half of it. And that's just the first layer of the story. Once the PAN precursor material is ready, it gets drawn out into long, extremely fine fibers. We're talking about strands that are almost invisible to the naked eye, thinner than a single human hair. Thousands of these tiny filaments get bundled together into what the industry calls a tow, essentially a thread made of thousands of individual microfibers running parallel to each other. These tows are the raw starting point for everything that follows. The spinning process has to be done under precisely controlled conditions. Temperature, chemical environment, tension, all of it monitored constantly. Because any inconsistency at this stage doesn't just affect one fiber, it affects thousands of them simultaneously. And problems that start here get amplified, not reduced, at every stage that follows. At this point, the fibers are still just PAN, still essentially plastic, still not anywhere close to the material you're imagining. What happens next is where the real transformation begins. And, fair warning, it's more intense than most people expect. Here's a question worth asking. If manufacturers could make carbon fiber faster and cheaper, why don't they? The answer is almost entirely sitting in this one stage. The PAN fibers get fed into large industrial ovens, continuously under carefully controlled tension, and exposed to heated air at temperatures between 200 and 300 degrees Celsius, and they stay there for hours. This process is called oxidation or stabilization. What it's doing chemically is rearranging the molecular structure of the PAN, converting straight polymer chains into a more complex, ladder-like structure that can survive what comes next. Without this stage, the fibers would simply burn up in the next furnace rather than transforming into carbon fiber. But here's the thing. This is described in research literature as the most time-consuming process in the entire manufacturing chain. It cannot be rushed. The temperature window is narrow. too hot and you create defects that destroy the fiber's properties. Too cool, and the transformation is incomplete. And these ovens run continuously, for hours, consuming enormous amounts of electricity, just to stabilize the fibers before the real heat even begins. This is the first thing manufacturers don't love advertising, because it reveals exactly why carbon fiber is so expensive and why cutting corners here is so tempting for cheaper producers. We'll come back to that in a moment, but first, let's talk about what happens when these stabilized fibers enter a completely different kind of furnace. After oxidation, the stabilized fibers move into the carbonization furnace, and this is where things get genuinely extreme. The fibers get heated in an oxygen-free atmosphere, typically nitrogen gas, at temperatures ranging from around 1000 to 1500 degrees Celsius. Why no oxygen? Because at these temperatures, oxygen would simply incinerate the fibers instantly. The nitrogen environment allows the heat to do its work without burning everything to ash. What happens inside that furnace is a molecular revolution. The heat drives off virtually everything that isn't carbon. Hydrogen, nitrogen, oxygen, and other elements get expelled as gases. What's left behind is a fiber that's now more than 90% pure carbon. The atomic structure has reorganized into tightly bonded crystalline formations, and those formations are what give carbon fiber its legendary strength. During this process, the fiber actually loses mass and shrinks. Remember how we needed 2.5 tons of pan to get 1 ton of carbon fiber? This is a big part of why. Material is physically being removed, vaporized out of the fiber as gases, leaving behind only the carbon structure. And for certain ultra-high-performance applications, aerospace, defense, advanced motorsport, the process doesn't stop at 1500 degrees. Some fibers go through graphitization, where temperatures climb all the way to 2500, even 3500 degrees Celsius. That's roughly half the temperature of the surface of the sun. The resulting fiber has an even more organized carbon crystal structure and extraordinary stiffness properties that standard carbonization simply can't achieve. This equipment doesn't run cheap. These furnaces cost millions of dollars. They run continuously, because stopping and restarting them mid-process wastes both energy and material. And the energy costs alone during these stages represent a major portion of the final price of every kilogram of carbon fiber you'll ever buy. After carbonization, you might think the fiber is ready to use. It isn't. Here's the problem. Carbon fiber in its pure carbonized state doesn't bond well with the resins and epoxies it needs to be combined with to create actual carbon fiber composite parts. The surface is too smooth, too chemically inert. You'd be holding incredibly strong fibers that couldn't bond properly with anything else. So the fibers go through surface treatment, usually a controlled oxidation process, exposing the fiber surface to chemical agents or simply air that roughens the surface at the microscopic level and makes it chemically reactive. Now, when the fiber meets resin or epoxy, it can bond to it properly. It can become part of a composite structure that works as a unified material. After surface treatment comes something called sizing. The fibers get coated with a thin layer of protective material, often an epoxy compound or nylon-based coating. This protects the delicate fibers during the next stage, which is weaving or winding them into ossable fabrics and structures. Without sizing, the fibers would snap and degrade during handling. Only after all of this, oxidation, carbonization, surface treatment, sizing, does carbon fiber become a material that can actually be used to make something. Okay, we promised you the thing the industry doesn't advertise. Here it is. The global carbon fiber market is controlled by a very small number of companies. Toray, Mitsubishi Chemical, Taijin, a handful of major Japanese and American manufacturers dominate the entire world's supply. This isn't just a fun fact. This is the structural reality of why carbon fiber prices stay elevated even as the technology matures. Because of this market structure, there's no aggressive price competition pushing costs down the way you see in commodity materials like steel or aluminum. Manufacturers who need high-grade carbon fiber, especially for aerospace, have limited options, and aerospace customers actually need consistency above all else. So suppliers prioritize stability and quality over aggressive pricing, and prices stay high. There's a second hidden layer, and this one's even more interesting. When you see a product marketed as carbon fiber online, especially cheaper automotive accessories, phone cases, or consumer goods, there's a very real chance that what you're looking at isn't genuine carbon fiber at all, because there's a widespread growing market for materials that look like carbon fiber, but are made from fiberglass mixed with dark pigments, or plastic films printed with a carbon weave pattern. They have the look. They have zero of the strength, and companies selling these products are rarely upfront about what they're actually made of. Real carbon fiber is 5 times stronger than steel, at 70% less weight. It genuinely outperforms virtually every conventional material in applications where strength and weight both matter. But that performance comes from the entire process we just walked through: the precise pan precursor, the hours of oxidation, the extreme carbonization, the surface treatment. cut any of those corners and the material you end up with isn't carbon fiber in any meaningful sense. And here's the number that brings all of this into focus. The entire global production of carbon fiber is only around 200,000 tons per year. Compare that to steel, where we produce 8 billion tons annually. Carbon fiber production, even after decades of development, is less than 0.1% of steel production by volume. That's not just a statistic. That's the entire reason it still costs what it does. That's the constraint the industry lives inside. Now that you understand the full process, every stage, every hidden layer, here's what all of this actually means for the future of this material. Here's the thing that stays with you after understanding all of this. Carbon fiber isn't expensive because companies are being greedy. It isn't rare because the technology is still primitive. It's expensive and rare because making it correctly, truly correctly, is one of the most energy-intensive, time-consuming, precision-demanding manufacturing processes on the planet. And every shortcut taken along the way produces something that looks like carbon fiber, but performs like a lie. That's the real hidden truth. Not some dramatic corporate conspiracy. Just this. The process itself demands so much energy, so much precision, so much time, that the price is almost unavoidable. And the market structure built around it means that price isn't coming down dramatically anytime soon. So the next time you see carbon fiber on a product label, whether it's a car part, a laptop shell, or a sports accessory, you'll know exactly what question to ask. Was this actually made the right way? Did it go through hours of oxidation, real carbonization, proper surface treatment, or does it just look the part? Because now, you know the difference, and that knowledge? Most people never get there. If this kind of deep research-backed manufacturing content is what you've been looking for, hit that like button, subscribe, and stay close. We don't do surface level, we don't do filler. Every video on this channel is built the same way this one was. Researched properly, explained honestly, and made for people who actually want to understand how the world works. Drop a comment below. Tell us which material or manufacturing process you want us to uncover next. Your suggestion might just become our next deep dive. See you inside the next one.